Okay, so yeah, I'm going to be doing an overview of the MMU and TLB system for BJX2. So, oh yeah. So in general, it'll use a semi-exposed and software-managed TLB design. So TLB entries will be loaded via a TLB miss interrupt. And yeah, page walking will happen in software, which basically means yeah. Um, so yeah, the basic interrupt mechanism will will it won't do all that much on its own. So um, the handler will have to itself do the page walking stuff or page table walking, and the ISR will always use physical addressing. This is yeah, again for the reason that um, because it itself has to handle the page walking and address translation. Um, yeah, it has to handle it like it can't actually operate in virtual addressing mode because that would potentially cause another TLB miss to happen, and if a TLB miss happens within a TLB miss handler, that's a situation that can't actually be resolved. So for that reason, the ISR mechanism will always have to be operating within the physical address space. Um, the conversion from virtual to physical addressing happens automatically, so it doesn't carry any runtime overhead in that sense. And it doesn't change any of the user visible state either. It will just, once the interrupt happens, it'll automatically be in physical addressing mode. We'll make use of dedicated instructions to load and invalidate TLB entries, namely LDTLB and INV TLB. Yeah, these instructions generally will take their input via registers, like fixed registers in these cases, but yeah. Does not expose TLB contents directly via MMIO. Yeah, doing so would expose a lot of implementation details, and it's more expensive than the use of dedicated instructions. In this case, the dedicated instructions will just sort of present something on the memory bus, and the TLB will see that happening and will act in accordingly. Similar mechanism is actually used for cache flushing and similar as well, so same basic idea. So in general, the MMU will support a baseline page size of either 4K, 16K, or 64K. This mode will affect the whole MMU, effectively setting the baseline. May also affect page table layout, though technically it would be possible to use a page table with a bigger page size within the smaller page layout, but this wouldn't really offer that much advantage. over, just using the larger logical page size. Yeah, larger pages can be emulated, whereas smaller ones cannot. Or, yeah, they can be emulated in the MMU. In this case, by doing multiple page loads for each subset of the page. And yeah, as noted, smaller ones cannot, for possibly obvious reasons. Maybe. Obviousness is debatable, but yeah. In any case, that's how it works. In this case, it's the baseline page size will effectively set the minimum page size for the MMU. The TLB currently consists of either 64 or 256 entries or slots, each of which is 4-way set associative. It's noted it's configurable and implementation dependent. So an implementation could have either a larger TLB or a smaller one than this, and could potentially have a different level of set association or similar. And be noted, the reason it's four-way set associative is because this turned out to be a reasonable compromise between being effective and also affordable. Something like a fully associative TLB would have been theoretically possible. However, even a design that's somewhat smaller would actually work out being like considerably more expensive than the larger set associative TLB. So that's why I went this route. Supported working set for the TLB is either 1 meg or 4 megs. For the 64, actually yeah, it's 1 meg for 64 entries and 4K pages, 4 megs for 16K pages, or 16 megs for 64K pages, or these other 416 or 64 megs for the 256 entry case. So yeah, the working set depends mostly on the baseline page size, which is the main reason you'd want to choose a bigger one, is to support a larger working set. So yeah, larger pages increase working set size, and as a result have fewer TLB misses. However, as noted, the downside of larger pages and the advantage of smaller pages is that there's less internal fragmentation with a smaller page. So in this case, internal fragmentation would refer to well, if you allocate 64K but you only need, say, like half of that or 3/4 of it, well then that space that falls off the end is pretty much wasted. So with 64K pages, that actually becomes a bit more of a problem than it is with either 4K or 16K. So it's one disadvantage I've observed with trying to use 64K pages. But 4K pages also have a disadvantage, which I'll get to later. So, current address space. The current implementation supports a 48-bit virtual address space. This could be conceivably up to 256 terabytes of virtual RAM. So basically, yeah, within that space, roughly about 3 gigs within the low 4 gig spaces usable for user land. Of this, like a good chunk of most of the remaining 1 gig would be usable for system use, and the final 256 meg is basically MMIO reserved. So that's how that works. However, yeah, there's another whole basically actually in this case it's roughly about 128 terabytes for the user land and another 128 terabytes potentially for system reserved space. Typically these addresses would be sign extended out to 64 bits, but currently the high 16 bits is actually ignored by the processor, so it's can go either way. One could debate the possible merits of enforcing that addresses were sign extended out to 64 bits and then check and raise some sort of fault or similar if there's a mismatch, but that adds cost, and I've gone with a slightly different route of, for now, defining that the virtual address space is, well, either 32 or 48 bits, but yeah, that's dependent on other control flags and similar. So you can set it up as a 32-bit mode, which would just straight up ignore the higher parts of the address bits, or it can be set as 48 bits, in which case it will ignore the high 16 bits. And at some future point, a full 64-bit version could exist, but I don't really expect much more than 256 terabytes of address space is going to be necessary within the near term future, because that's kind of a lot. And it's for a single process, it's not hard to exceed the 4 gig limit, and for an entire system it's pretty much guaranteed you're going to exceed 4 gigs with current memory use. But for an embedded system, that's probably sufficient. So yeah, in the current implementation, there's a 32-bit physical addressing space, which can generally allow up to about 4 gigs of stuff in it. Of this, at present, roughly about 29 bits of space is reserved for use by RAM. This is roughly the 16 meg mark up to I think 448 megs or something like that, if I remember correctly. But either way, yeah, I forget right offhand, but yeah. In any case, yeah, it's roughly a little less than 512 megs is available for use by the RAM, but that's not really too much of an issue right now, because yeah, within the region reserved for RAM, physical RAM addressing effectively wraps around. So if you have yeah, say in the Nexus A7 there's 128 megs, but after the 128 meg mark, then the RAM will effectively wrap around back to the start again, and it will repeat several times over the course of this area. But this is currently now the emulator emulates this behavior as well, so it can be used for like things like determining how much RAM there is, because if you write something and at the low end and stuff, once you see that once you see the same contents repeat again, then you know that effectively the RAM is wrapped around, and you can use that as your RAM size limit. So it's one possible implementation. The other of which is, you know, detecting an address where yeah, another implementation would have been detecting an address where upon writing to that address no longer has an effect, and it just returns some default uninitialized value. But in this case it, you know, uses wrapping behavior. And the board I'm currently testing with has a 128 meg RAM chip in it, so yeah, this is plenty. And comparatively, the this huge virtual address space is completely overkill for probably for something with only a 128 megs of physical RAM in it, but it allows room for expansion, I guess. Currently, there's a roughly 28-bit region reserved for MMIO, so basically, yeah, the high 256 megs of the low 4 of the lower 4 gigs are used for MMIO addressing. This would include various hardware and other stuff like that, which is handled specially on in the bus interface. So yeah, so RAM and MMIO are currently treated differently by the bus. In this case, RAM is generally handled by moving cache lines around, whereas MMIO, it's effectively moving discrete word values, either double word or quad word values per bus access. So, and RAM uses like L1 and L2 caching and so on, whereas MMIO completely bypasses caching. So it's effectively a different mechanism almost. It's actually almost more like the IO port interface for x86. It's, you know, just sharing the same bus signaling with the RAM bus. So yeah, that's how that works. So within the TLB, as noted, it consists of entries. Each entry corresponds to a logical page, and each of these entries is 128 bits. So we'd have roughly the high 16 bits encodes what's known as the VUGID value, which I'll get to later. So it's, yeah, and there's 48 bits for the virtual address for the page, another 12 bits for basically the keyring access mode, another 16 bits which is either available or can be used as an address space ID, which is kind of a semi-useful feature. And there's a physical address space, or where this address range maps to in physical RAM, and then some page control bits. Not all of this is stored directly in the page table, but rather some of this is actually synthesized via the, or actually a lot of this is sort of pulled together via the TLB miss interrupt. So when that happens, it'll unpack the page table address and some information from the interrupt itself to generate this contents. The VGID entry itself consists of basically a GID or group ID and a UID, or could be considered a user ID, but actually in the way it's used is these two are more closely related to a PID or process ID. Going to get to how all this fits into the memory subsystems at some later point, but for anyone familiar with like Unix style file system protections, this is probably pretty obvious where this is going. So there are keyring access modes. It's basically a set of read, write, and execute. So for each of these, the levels it can match, you have well, if both user and GID match between the page and the current keyring, then it'll use these flags. So basically, whether the particular user can read, write, or execute the flag or the page, then whether if they don't match, if UID doesn't match, it'll be whether the group can match, and if neither matches, then it'll be other, which will basically function as the equivalent of the global page access flags. And there's also the mode, which partly influences the way these other flags are interpreted in relation to the keyring register. So yeah, this stuff isn't actually mandatory, but it can be turned off, in which case it will function more like a more traditional MMU, and you can, not bother with, page level access control in this sense. It'll just be the normal user supervisor system, which, has its bits over in the page control bits area. Yeah. And as noted, being four-way set associative, there would basically be 4 TLB entries packed end to end within each sort of table index. And when it tries to match a page, it will see if any one of those 4 is a match. If so, it will basically use the matching TLB entry, or failing that, it will generate an interrupt, so that the interrupt can get the appropriate entry loaded via some mechanism or another. generally involving a page table. But yeah. So page table layouts. As noted, there's currently 3 different page sizes available, and for these generally several different page table layouts are being used. As noted, can be noted, the page table layout does kind of have to match the size of the logical page being used, but yeah. So there's a more traditional 4K page like what you'd see on, you know, most x86 or ARM style systems. Well, except like they have more page table layouts in this, but you know, same basic idea. So yeah, have 4 levels, each of which has 64-bit entries in the page table, and 512 of these entries per page. And you know, with 4 levels, you get a total of 48 bits of address space. So that works out okay. 16K pages, it's basically 3 level instead of 4 levels, and with more entries per page. But annoying as it turns out, this layout doesn't correspond exactly to 48 bits. However, despite that limitation, you still can get a full 48-bit address space by effectively using 2 page tables, like one for the user land and one for the system land, in which case you still get the same full 48-bit addressing space. So this one works in that sense. 64K pages. For this, you only need a 2-level page table with, you know, 64-bit entries and 8,000 of them per page. But so yeah, you only need 2 levels, but at the same time you only get 42 bits of address space, or roughly about 4 terabytes, which is not nearly as much. But as noted, that's probably more than sufficient for most of what this will be used for. So yeah. And specific subject to page walker algorithm. As noted, since the page walker is implemented in software, you can, you know, use different page table layouts if you want, or use larger page table entries, or you know, add another level of, or another mini page type level to make up the difference, or whatever else. Because it's implemented in code, the code can do pretty much whatever here, at least as far as the CPU is concerned. Technically, you don't even necessarily need to use a page table directly. You could actually say have a much bigger TLB that's implemented in software, and then just, you know, use a 2-stage TLB via the miss interrupt handler. But various possibilities exist. I had sort of wanted to put the page walker in the ROM. However, in the current implementation, I've ended up putting the page walker logic in the kernel and stuff, because, like, of, well, more subtle reasons. Partly it's because partly it involves, like, how to signal back to the or back to the OS kernel, how you want to handle page faults and similar. So it's easier, admittedly, if you have the page walker in the kernel rather than in the firmware. But the firmware's option is more of a intermediate for if you might want to have the page walking algorithm in hardware, like it's like on some other more popular architectures like x86 or ARM, which don't which don't make use of interrupts for TLB loading. So yeah, it's a trade-off. So as noted when I was testing with Doom before, with 4K pages you can sort of adjust the TLB to get different miss rates. With the current setup, with 256 entries, each of which is 4-way associative, that works out to an average miss rate of about 100 or 198 TLB faults per second at 4K byte pages, which is arguably like not too bad, or not all that bad, because well, the handler doesn't take that many clock cycles, so, and a few hundred of them per second isn't that many. Whereas when you start getting into the thousands, then you get into problem area. And for really small TLBs, it runs into a problem that, while it seems like it's starting to level off, that's actually mostly because most of the CPU time is actually going into the TLB mishandler. So it's performance is pretty bad in this area. So kind of don't want to do that. On the other side, it never drops off completely to zero either, because in this case it seems that basically pages are knocking each other out of the TLB fast enough to well, to where it never completely levels off, even if you make the TLB a lot bigger. It's probably a limitation of being 4-way set associative, I think. But so that's, yeah. But in any case, it's not too unreasonable. So yeah. So 64K pages, as noted, well, your average miss rate is quite a bit lower. It's still pretty bad for if you want a really small TLB, like say less than 16 entries. But yeah, say 8 for 2 entries. Well, yeah, you can see what's going on here. In this case, it's one entry with actually one slot with 4 TLB entries in it, so it's only 256K in total, and then you're rocking out at nearly 100,000 misses per second, and yeah, that's not good. And in these lower ends, despite it having a non-zero value, the actual effective hit, like miss rate, is almost zero on average. So you'd actually only be seeing a TLB miss like once every few seconds or so, with them only really spiking up whenever a new map is being loaded. So works out reasonably well. But as noted, even with 64K pages, if you rank or rack up the TLB size, it still basically goes into diminishing return territory, so it's not possible to entirely eliminate TLB misses even with 64K pages. But it drops down to an acceptably low level. Oh yeah. However, the big downside of the 64K pages is because frequently only part of the page is actually being used, or parts of the page are being used. There's a bit more of a problem with internal fragmentation or memory waste. So yeah, 64K pages aren't necessarily a winning situation either. So this is where 16K pages came in as a useful compromise. So so with a 256x4 setup, it worked out to about 17 misses a second for running Doom for 1 minute, or for starting it up and running it for 1 minute, or 5.2 misses per second for starting it up and running it for 3 minutes. This is because initially there's a higher amount of misses when it's actually loading up Doom and similar, but once it's fully loaded, then it settles down a little bit. But it seems to be a reasonably good compromise. Has a fairly low average miss rate, more like the 64K pages, and has a fairly low fragmentation overhead, more like what's seen with the smaller 4K byte pages. Works out reasonably good in that area. Not necessarily the case that it would hold up for other programs besides, well, Doom and so on, but that's what I'm testing with. And in general, at least, things that hold up reasonably well for one program tend to hold up reasonably good for another program as well. So consistency in terms of like major like abstract features is seems to be reasonably good. Different programs will do things slightly differently between them, but they'll tend to be roughly similar in terms of general attributes. So yeah, there will be a virtual memory subsystem, and there will be a page file on the SD card, which is, as noted, well, yeah, people should probably know what a page file does. But yeah, a fixed region of RAM will be used for mapping VM pages into memory. In the current implementation, this is set up for it'll grab a chunk of about 32 megs, and that will be used for pretty much all of the virtual memory. This might be increased in the future, but for now this is what I'm going with. So whenever needed, an old page will be evicted from RAM and stuff, and then a new page will be loaded into the same physical page. So it will effectively be recycled as if it were different parts of the page file, and with all the associated page table wrangling and TLB flushing that will be necessary to make something like this work. But yeah, all VM pages will have dedicated backing store, a dedicated backing store location in the page file for, probably obvious reasons. The fixed RAM region won't actually be used much like traditional RAM, but will actually exist more as a series of like small windows into the page file, as it were. May be subject to fairly high paging costs. For potentially obvious reasons as well, whenever a page is accessed that's not currently in RAM, it might actually have to, straight up write an old page back to the SD card and then load a new page from the SD card, which is not a particularly cheap operation, and not exactly a particularly fast operation either. So as a result, real-time tasks should not use virtual memory. While it might seem like using any virtual memory on the system might be a deal breaker for real-time tasks, if you're scheduling them via either interrupt handling or via some other sort of interrupt driven scheduler, then as long as they're present in physical RAM and also, and assuming the page, or the page flush and page writing and reloading logic itself isn't entirely running in an interrupt handler, then it should work. It should still work okay. In this case, once the TLB miss interrupt handler realizes that it doesn't actually have the needed page in the page table, what it will have to do is it will effectively do a mode change from the interrupt handling mode back into essentially a supervisor mode or system kernel mode, which would have interrupt handling and virtual memory and similar re-enabled. So then once it's in that mode, new interrupts can go back to the interrupt handler, but the system kernel handler will be able to load and save pages and so on as needed to implement the virtual memory subsystem. And if if an interrupt for a real-time process would happen to come along, then it can quickly switch over to handling that task without that task necessarily having to wait for the page table operation to finish doing its thing. So but that is of course predicated on the whole sort of premise that your real-time task cannot use virtual memory to do so, because, well, reasons for that should be pretty obvious in this case. How the virtual memory will be handled in Testkern for now. Current plan is to basically use a single unified address space. So rather than most other operating systems, which will give each process its own little virtual address space, it'll just sort of use a giant unified one. This is partial reason it needs like a 64-bit addressing, even with the relatively small amount of RAM in the boards and similar, is because of the use of a unified address space. So as noted, all logical processes will exist within the same address space. Yeah, that's self-explanatory enough. The same C ABI, namely the PBO ABI, will be used as in the no MMU case. This is partly for various reasons, but real-time tasks that aren't using virtual memory will effectively need to operate as if there was no MMU at all, pretty much. So that kind of follows. And in the case of logical processes using the larger virtual address space, the same no MMU model still makes some sense in this case. This is because in order to implement the more traditional model, namely with only using base relocation and similar, you would effectively have to double map all the executable or multi-map all the executable sections into multiple places, which is kind of pointless and wasteful, but not as bad with an MMU present. But it's basically unnecessary if you're using a no MMU ABI. For those familiar with it, the PBO ABI is vaguely similar to something like the ELF FD pick ABI, but differs quite a bit in terms of the implementation details, namely that it's basically daisy chaining via the base or global base register rather than having having a bunch of global offset tables that are sort of daisy chained together. But so it's functionally different, and it has a lower overhead as a result, namely that you only need to reload the global base register when you're calling between one executable image and another. And if you have some idea when that happens, then you can greatly reduce the number of times you need to reload it, and internally everything functions roughly the same as it would in a direct linked case. You do kind of have to have the binary set up in a way to where they can be loaded pretty much anywhere in the address space, which is unlike some traditional forms of exe files, which are designed to only be really loaded at one particular address. But so yeah. In my case, I'm using a variation of PECOV, so there's still the base relocation table, which is effectively present in all the binaries, and it's used to fix it up to where the base program or base image is loaded in RAM. So it's the base location for the executable code, whereas all the data and BSS sections and similar may be located elsewhere, pretty much anywhere in RAM, and they're just sort of daisy chained together on their own. No, the low 4 gigs of address space will be used for physically mapped page ranges. So yeah. So basically, yeah, if you just want to memory map one section of pages to another location, this can take place in the low 4 gigs, but this isn't actually virtual memory because it's not actually back to the page file. So it has some practical limits there. And yeah, so yeah, these pages are remapped, but only correspond to other pages within the physical RAM area, as opposed to, well, page file stuff, or MMIO, which in my current design can't actually be is unable to be remapped via the MMU. So that might change in some future implementation, but in the current implementation, the MMIO ranges are pretty much hardwired. Addresses past the 4 gig mark will be used for virtual memory, and these ones will all be mapped to pages in the page file. It could have been done differently, but this is just the route I decided to go with in this case. But this does implicitly mean that any programs that can be used with virtual memory will need to also use 64-bit pointers, whereas programs whereas real-time tasks and things of that sort might conceivably be able to get by using the slightly narrower and cheaper 32-bit pointers. So now, I had been working on trying to make it where the kernel can support binaries that are compiled in either mode, with the kernel generally being compiled with 64-bit pointers probably. Unless, of course, for an implementation that doesn't have an MMU, in which case then it's kind of pointless to use full 64-bit addressing. So there's some trade-offs there. Oh yeah, the BJX system. Any more to say on this? So yeah, there will be the BJX or keyring register system, which is primarily intended for virtual memory protection. So, and also relatedly, that's why one might want to remap physical pages in RAM, is because remapped pages can make use of the BJX system, whereas in physical addressed ranges that doesn't actually make all that much sense. So that's partly what this is for. So each page can be assigned a UID and GID pair, and has some dedicated access control mode bits. So mentioned that earlier, and as noted, it's basically the same idea as Unix style file protection in that sense, but it's handled a little bit differently in this case, in terms of the actual checking. And a keyring register is used for access checks, which may contain up to 4 different pairs, with the 00 case being treated as a null pair. This would be used for entries which aren't present, or if the key ring isn't used at all, then it will only consist of null pairs. That would affect that case effectively disables the key ring checking, which would be useful for like more things like the OS kernel and similar, which probably doesn't need to be using keyring checking. So to access a page, at least one of these pairs needs to match, and it sort of ORs them together in terms of the access rights. So if you're trying to read a page and if any 4 of the entries in the keyring register have read access, then you can read the page, or if any one of them has write access, then you can write the page, and if any, and so on. The keyring may be empty, in which case it falls back to more traditional page checks. Well, like you would see in something like x86 or ARM, where it will check for user or supervisor access and whether you have read, write, or execute privileges. So yeah, and in order to grant access, it will be an AND match with the VuGet access. So the VuGet access can't or is unable to grant any additional privileges or access. Yeah, any additional access privileges over what you would have with the baseline checks, but it's mostly used to further restrict what a given piece of code is allowed to do. Each logical process will have its own VuGet pair. Again, this is partly what it's being used for, is essentially it's, you know, to isolate each process to its own local memory. So despite so it's needed to, you know, provide memory protection in a shared virtual address space, and yeah, design takes inspiration from Unix style file permissions. So yeah, as noted, if you don't have something like this, then with a single large address space, you either have only the user supervisor split, like say the kernel can protect its data and stuff, but you couldn't protect anything in user land from anything else in user land. So if it has access to the pages, it can do whatever with them, which isn't really, you know, all that useful if you're wanting to stick several different programs in the same address space, because you sort of don't want them to be able to directly stomp on each other's memory. So it makes sense to have sort of protection scheme to protect them from each other. And despite its being named as user ID and group ID, it's actually will be more functionally similar to a PID in this case. But it'll actually partly overlap with the PID system. So the PIDs might, though this part's not fully done yet, the PIDs may or may not be treated as VuGets. So yeah. Or actually stated more the other way, the PID might actually just sort of be the two fields bit packed together. So yeah, but same basic idea. Trying to think of if there's anything more I need to say on this. Yeah, this is. I'm not sure offhand if anyone else is doing virtual memory protection this way, but kind of makes sense in this case, and it's debatable whether this system will be strong enough to handle actual malicious code or anything like that, but for now it's more sort of being intended to deal with general memory stomping concerns and similar, as opposed to trying to be like a protection mechanism for sandboxing things. If you wanted to have transitions between different logical processes or similar with their own address spaces, you'd essentially have to do something like a set UID mechanism. I've yet to come up with a mechanism that's both strong and effective at this task. I've come up with a few mechanisms which could be able to do it reasonably quickly via essentially using encrypted keys, which would be decrypted and reloaded at run, or yeah, by the hardware and stuff, but that has the problem of that it's fairly limited in both in terms of capability and effectiveness, namely that like the encryption used for the keyring reloading is painfully weak and could be brute forced, almost immediately by any code that was actually malicious. So not terribly useful for actual security. The alternative is of course doing the transitions via interrupts, which more or less can be enforced by the current design. So in that case, you would initiate an interrupt to be able to transfer from one area to another, and then it's left up mostly to the kernel to reload the keyring register and other things as needed. But those are the options that are currently available for this. As can be noted, the hardware level version can be effectively either enabled or disabled, and if it's disabled, then it's not possible to be for it to be used for reloading the register, in which case you essentially have to use the interrupt, but it might be a useful feature to have a hardware version for like some later point. Yeah. As noted, as can be noted, like, yeah, reloading the key register would be a lot cheaper and faster than having to actually change the address space, which involves completely flushing the caches and TLBs and other stuff like that. So, yeah, don't want to do that casually. You want something that's, cheap and simple, like reloading a register. Similar reasons for why I'm going the whole like single giant address space route in the first place is mostly because that should be more useful for for having real-time tasks involved, because then you don't have, or then you effectively don't have any need to change address spaces when you're switching from switching from normal execution over to a real-time task. So it can just, get triggered and go, at least barring any TLB misinterrupts or similar. But so it's, that's a lot lower overhead than, something like needing to reload the whole address space first. And for something like motor controls, you might be getting a lot of interrupts fairly quickly, and you might want to be able to handle them quickly. Yeah, as can be noted, like, yeah, you might be getting timing either from the main timer interrupt or possibly from watchdog interrupts or other things like that. So say like you set it up to where after a few microseconds or so it'll trigger the interrupt it needs to trigger in order to handle the given event. Like say every few microseconds you want to step the position of one of the stepper motors or something like that. So it's part of what I'm designing this for. Well, never mind like this whole architecture being all VLIW and SIMD and having SIMD and similar, which is more intended for DSP tasks. So kind of an oddball thing, but yeah, it's a combination of a vaguely semi-general purpose, semi DSP use case. But yeah, I think I've mostly about handled what I was going to, or mostly talked about what I was going to talk about for now. So yeah, I think I'm gonna call it.